Hello everyone, we are Group 13 and our topic today is temperature distribution in a city, focusing on the urban heat island effect. Let me kick things off with some shocking real-world data first. Okay, first, what's an urban heat island? Simply put, city centers get way hotter than surrounding rural suburbs. Let's look at real cases. In Beijing 2023, downtown temperatures were 3.5 degrees Celsius higher than suburbs, hitting a peak of 42 degrees Celsius while suburbs only hit 38 degrees Celsius. Tokyo's situation is even worse. In 2025, the city core was 12 degrees Celsius hotter than the nearby countryside. On average, major global cities have a heat island gap between 5 to 10 degrees Celsius. Worse still, extreme heat events have jumped by 30% in frequency recently. These rising temperatures aren't just uncomfortable. They bring a whole list of serious problems which my teammate will break down next. Before I hand over, just a quick frame. We won't only talk about environmental issues today. The highlight of our project is using calculus technology to build a mathematical model that simulates city temperature changes. Over to you, Shao Junxin, please.
Thanks, Zhou Peixuan. Let's start with the four major negative impacts of urban heat islands. Number one, skyrocketing cooling energy use. More heat means everyone cranks up air conditioners, which burns more fossil fuels and create more human-made heat in vicious cycle. Second, huge public health risks. High heat triggers heat stress, worsens cardiovascular diseases, and pushes up hospital admissions during heat waves. Third, air quality gets worse. Hot, stagnant air traps pollutants like dust and exhaust fumes right over the city instead of letting them disperse. Fourth, economic losses. Workers become less productive under extreme heat, and high temperatures put extra stress on roads, power lines, and public infrastructures. To analyze and predict this uneven temperature distribution, we rely on four core calculates to multivariable tools. First, partial derivatives. They measures how temperature changes separately with local or time, ignoring other variables temporarily. Second, gradient vectors. This vector always points to the direction where temperature rises the fastest, super useful for spotting heat hotspots. Third, total differentials. They calculate the combined temperature change when multiple factors shift at once, like wind plus building density. Fourth, the heat conduction partial differential equation, the foundation of our whole city temperature model. Also, city temperature is a multivariable function written as T of x, y, z, and T. T stands for temperature, x, y, z are spatial coordinates, and T represents time. Every spot's temperature depends on where it is and what time it is. Now, Speaker 3 will walk you through our full mathematical model and concrete calculation examples.
Okay, alright, let's dive into the math part step by step. Our core formula is the heat conduction equation, which is shown on this PowerPoint page. And let me quickly explain each part. Txyzt is our temperature function. A is thermal diffusivity, a fixed property of ground and building materials. Q is the heat source term, covering solar radiation heat from cars, factories, and buildings. Our model also considers boundary conditions, building height, street width, surface reflectivity, called albedo, and green vegetation that cools cities via plant transpiration. We simplify the city into a two-dimension temperature field for easy calculation with a function Txy. Here is the function. Firstly, we compute partition derivative to find temperature trend rates. Next, we set derivative equal to 0 to solve for critical point where temperature stops rising or falling. After solving the linear system, we get a critical point at negative 68.2 and negative 72.8. This negative coordinate spot is outside the city, which means the temperature minimum is in rural outskirts, exactly matching the heat island theory. Heat peaks in a positive coordinate urban core. Then we calculate the gradient vector at the city center point. With 50. Plunging in the numbers, we get delta T equals to 3.5, 2.5. The magnitude is around 4.3 degrees per kilometer, and the direction is 35.5 degrees from the x-axis, pointing northeast. This telling us temperature climbs fastest toward the northeast of downtown, which is our main heat accumulation zone. All our math results match real observed data from Beijing, so the models work reliably. Now, Speak 4 will share real-world solution model flows and our final takeaway.
All those calculus calculations aren't just abstract math. They directly get urban planning and heating mitigations policies. Let's go through 3 actionable strategies supported by our parameter-sensitive test. First, building density controlled. Every 10% rises in building density pushes temperatures up 0.8 to 1.2. So cities must enforce minimum green spaces radius in dense downtown zones. Second, expanding mitigations. If green covers hits 30 to 40%, heat island intensity drops by 20 to 30%. We can build green mitigation corridors, follow the gradient directions we calculated to block heat flow. Third, high elbow construction materials. Switch serviced urban least 0.1 to 0.3 causes peak temperatures by 2 to 3. So the new building should be required to use a reflectable fluting and pavement. We can also design street layouts aligned with wide paths to boost nature cooling. Let's state our current model has clear limitations. We only use 2D flat analysis and ignore vertical temperature layers between tall buildings. We assume uniform surface properties everywhere and leave out daily. Seasonal temperature shifts plus tiny macro-leveled efforts like building shadows. For future research, we can upgrade to a 30-time dependent heat equations, combine fluid dynamic for wide simulations, uses finite element methods for complex city shapes, and even added machine learning to optimize its model parameters. We can also build multi-scan models covering street canals all the way to whole cities, plus integrate human servo. So to round up our presentation today, urban heat islands are several global climate issues, and the metaphor calculus give us powerful tools to quantify, visualize, and predict uneven city temperature distributions. Our mathematical model successfully reproduced the real heat island patterns, and the gradient analysis give clear evidence-based guidelines for city planners to cool down overheating urban areas. If we combine street grading spaces rules, reflectable construction materials, and optimizing fertilization correct design, we can effectively reduce urban heat risk for all residents. And that's all for our presentation. Thank you for all listening, and we are ready for any questions.